Fine. Okay, let's begin. A few minutes late, but if today's class is rather small. I would say it's an interesting topic. It covers how the vertical stress is distributed in ground. So if you have a case where the ground is loaded and you're looking at any stress distribution, we are mainly interested in vertical stress distribution. So this part of section will only focus on vertical stress, that too for an elastic. Our focus is elastic material, and you would be surprised that such an assumption, if you use for soils, you're not really too wrong. So our topic is how when a load is surface is loaded and what happens in the ground. So I've taken an example. The very first photograph over here is a photograph of a small container. Okay, hardly less than half a meter wide, but it's a small container on a laboratory floor, and it's been loaded by a stack of weights and distributed probably over a plate. Plate is not visible. So our first focus, let me move on to the next slide, is what happens if the loaded area is large compared to the thickness of the ground. So in the photograph which was shown, apologize, let me right click and okay, it's already, you can download the photograph. You didn't tell me. Okay, so okay, so what happens for the case when the ground, the example which we had on the photograph, that the thickness of the clay layer is comparable to the loaded area. Okay, so if I go back, the loaded area was probably around this wide. The thickness of the clay is this much. So if I say the thickness of the clay is equivalent to, or let me just put it in as a thumb rule, is comparable to. In most of the cases we say if this width or this thickness is less than equal to the loaded area, in that case whatever is the load you apply on the surface. When I say load, I mean the pressure. Whatever is the pressure you apply on the surface, it is safe to assume that the same pressure, vertical pressure, exists in the ground throughout the depth. So in that case, the particular previous case, we had an example of a loaded area over a thickness of the clay. We can safely say whatever is the applied pressure is the same pressure in the ground. In fact, that example was for a laboratory test, but you can safely take that example, extrapolate the example for field. So if you're looking at a large embankment over the ground, okay, and you're looking at how the vertical stress is distributed in the ground, an example is an important case if you need to look for settlement. You're looking at settlement, mainly consolidation settlement or even elastic settlement. It's important to know what is the stress distribution. So in that case, loading is considered to be the same. This is called as one-dimensional loading. So there is no I would say increase in stress with depth. The stress remains the same. For a limited loaded area, so if you're looking at a case where your loaded area is small compared to the thickness of the soil. So take an example of a footing, maybe a strip footing or a square footing, any kind of foundation I would say, and your thickness of the zone is large. In this case, the loading is considered to be two-dimensional, and you need to look at what is the stress below ground. The stress is definitely different, and we're looking at this case when you have a finite loading. Finite meaning it's limited loading area compared to the thickness. Take an example of this figure which is shown on the top right. Okay, please concentrate on top right figure. Okay, top right figure, you have a force P which is applied over a footing of B, and possibly the one this footing is long, so we call it as a strip footing, and it's one unit which comes out and hits you. So assume that the area of the footing is B times one unit which comes out and hits you. So in that case, the vertical pressure you apply on the surface is P divided by the area. over here we have written stress, okay. Now I would like to emphasize that this word is incorrect. You don't apply stress over the ground or over any material. What you apply is pressure. Stress is something which is manifested or developed within the system or within the ground. So when I apply pressure, I only apply load or pressure, but I don't apply stress. So I believe I've got this wrong over here. I would request you to correct this. This should be pressure. So sigma naught is the pressure you applied. P divided by the area, which is B times 1 unit, which comes out and hits you. That's the pressure applied on the footing. So if this footing is finite compared to the thickness of the ground, so we have a load distribution. And the most common load distribution which is used is 2:1. Okay, so 2:1. If you what it means is you go down two depths and horizontally the load is spread by one depth. So in this example, it shows that we are interested to know what is the stress induced. Remember, now I use the word stress induced because it is manifested or developed in the ground. So what is the induced stress at a depth Z? It would be I go down Z, so I go off by Z by half on one side and Z by half on the other side. Okay, so that is the widened area, right? So in this case, what is the stress induced on this surface? Again, I have the load which I have applied, which is again P. Okay, P in this case equals to it's shown by this whole lot. P equals to the pressure on the surface times V times 1. So that's P. Why we say P? Because the force, whatever force you apply at one end of the material, the same force gets developed at the other end. The force doesn't get lost. It's the pressure which gets lost or dissipated. So that's the force we have applied divided by the new area. In this case, the new area is B plus Z by 2 plus Z by 2. So it's B plus Z, that's the whole thing, times 1 unit which comes out and hits you. Okay, that's the stress induced. Now in this case, the stress induced is on this level, and we have taken 2:1. Let me emphasize that 2:1 is the most commonly used method, but if you follow IS code gives a range of angles. So some code, in fact, for some soils it says 45 degree, the spread is 45 degree, or you can even go down to 60 degrees. So 60 degree will be more pessimist. Okay, so you narrow down. But nonetheless, whatever the rule you choose, you would not be very far off from the answer. That's the emphasis of this point. And most commonly, why I say 2:1, because the many geotechnical reports you will find in practice when you go out after graduation or post graduation, you'll probably find reports in which 2:1 is commonly referred. Why? I would say possibly because you can do a simple hand calculation to solve for this. Otherwise, there is no hard and fast rule to choose any other load distribution, as long as you clearly state what is the distribution you have taken. Okay. Now the top figure was an example of a long strip footing. Okay. Now the question comes, when does a footing become long strip? And the bottom figure is a rectangle footing. So rectangle means the width of the footing is still the same. So it's shown over here. Whereas the L is finite, it's limited now. Okay, L by B is the area at the top. Now the question comes, when would I consider this to be a long strip footing and when this is a finite footing? Now over here I would say your guess is as good as mine. There's no hard and fast rule. I have referred to many textbooks, there's no hard and fast rule. But as a thumb rule again, many engineers consider that as L becomes more than 4 or 6 times B, it's quite convenient to consider this to be a long strip footing. Okay. Now in this example, I have L by B at the surface. So what is the applied pressure? Again, this word is incorrect. So I should correct myself. So the pressure applied on the surface is the load P divided by the area, which is L by B, L times B. Apologize, L times B. So if the 2:1 would mean, if I follow this analogy, I go down depth Z, I'm interested in what is the stress induced at this depth Z. I look at a dimension which is now B plus Z. If you recall, this is the same logic which has been used from the top figure. And the other dimension is L plus Z. That's the other dimension. So the pressure, or I must correct, this is the stress induced at this level would be the force, which is again P, which equals to sigma naught dl. That's P sigma naught dl. That's the force I have applied. Remember, the force never gets dissipated with depth. It remains, divided by the new area. The new area is B plus Z times L plus Z. That's over there. I'm not sure if you can read it, okay, but that's quite simple to understand, okay. So having said this 2:1, it's good idea to look at what we normally would like to follow in case we look at an elastic material. Remember we said in theory of elasticity, you can use the principle of superimposition, meaning I apply load at one end and measure the deformation. It is the same as I apply fraction of the load, the deformation would be similar fraction. So it merely means that theory of linear elasticity exists. Okay, so I can apply load in parts, apply load in full. My deformation or displacement would be again in parts and full, and that's the theory of superimposition. So if you're not very familiar with this, I request you to refer to a textbook. A commonly used textbook is by Timoshenko. It's interesting to look at theory of elasticity. So in this case, we use Bossy's theory. So Bossy's stress distribution, there are a few assumptions, and I would like you to look at, okay, figure is not clear. Okay. Someone says figure is not clear. That was previous slide. Previous slide. Okay. So I hope that figure is now clear. Okay. You can click on it, but I hope you have understood the point. Come back to this slide. Okay. The assumption made is for elastic theory of elasticity. Assumption made is the soil is homogeneous. Okay. So homogeneous means it's the same properties exist throughout the medium. Isotropic. It's a good way to understand. Isotropic means whatever are the properties in one direction, the same properties exist in the other direction. That's isotropic. Linear elastic half space. Why we say half space? Because the ground we assume to be half space. Above the ground is air. So that's half space for us. Soil is weightless. So we do not take into account the weight of the soil, and unstressed. So initially there is no stress on the ground. The other assumptions are foundation is flexible, and because of this flexible footing, the contact pressure between the foundation and soil will be uniform. Had the foundation been rigid, you would have had uniform settlement, but in this case the contact pressure is uniform. So the vertical stress for a point load which acts perpendicular to the surface, okay, is, take this cartoon on the right, top right. So I have a vertical load Q, point load, which may be in kilonewton or kilogram, any unit you prefer. That's the load on the surface, and we are interested in sigma z, which is the stress induced at a depth z and a radial distance x. Okay, so horizontal distance is r. I must say this is the radial distance. Sorry, radial distance r and depth z. X is the diagonal shortcut, most shortest point, or the hypotenuse. I think it's hypotenuse. So z and r. Okay, so we have an equation over here. I'm not sure. I'll just zoom in. Oops. Okay, so that's sigma z, stress induced at a depth, which is again r square plus z square whole to power 5 by 2 in the denominator times 3z cube by 2 pi. Okay, now this is for Bossy case if you have a point load. We will not go to derivation for this equation. So I therefore request you to take this as a tablet, just take it as it on the face value. Okay. So for this what was case for the point load. If you are interested for the case when you have a other loading situations, let me zoom out please. Yep. Other loading situations, for example a line load would be the case which comes out and hits you, that's the line load. Uniformly rectangular load and trapezoidal load. Again all these equations or distribution are based on, you integrate this equation over there. We will again not go into this derivation, but take the face value of the line load or the rectangular load in the next few slides. On this slide I would like to introduce a term which is commonly used in pressure distribution or stress distribution in ground. And the term, it's best to understand how you look at the equation. This is the Bossini's equation. Okay, ignore everything else. So this equation, if I look at the figures on the right, if I have a plot of, again I need to zoom in, sorry I'll just zoom in. That's the, so in this case I have a plot of sigma z by q on the vertical axis and I vary the results with radial distance. So I keep z constant, depth constant, and look at how does this load, now remember the sigma z by q, how does sigma z by q vary with radial distance. I also have this kind of distribution. Again on the other hand I keep the depth, I vary with depth. So that's the depth on the vertical axis. Again sigma z by q, I have the same value but this time on horizontal axis. Okay, and I vary by keeping the radial distance constant. So that's the another set of plot. Right. Now what happens if I combine the two plots? I'm going to zoom out. Okay, if I combine these two plots, okay, I'll come to these figures later. They're just numerical finite element results, not interesting. But what happens if I combine the two plots? Remember I have this plot which is somewhere over here. Okay, I have this plot which is again one of the lines is somewhere over here. So shaded region over here and perhaps shaded region over there. If I combine the two, I have points, these points over there. For example, this point which is shown over here, which I connect such points together, you will find that all the stress in this zone is same, is constant. So sigma z, so remember is here and there, sigma z is constant. So I combine these 2 points. Again I vary with depth and I get this kind of bulb. It's a shape of a bulb. So we don't mind calling it as a pressure bulb. Okay. Many times we call this as an onion shape, onion. It was used to be expensive a few months back, but it's damn cheap now. So that's onion shape for us. So there's no harm in calling this as onion shaped bulb, but to give a rather nice name to it, we say iso. Iso means same, bar is pressure. So it's usually called as isobar. Okay, isobar or pressure bulb. Okay, that's one term which we have. So such isobars, let me go back, you can easily produce by using any finite element tool. Now we have a lot of tools which lot of tools which merely work on click. You just click and it works. Okay. Now I have an expression for line load. Let me zoom in please. Again this is we are looking at stress distribution at depth z and radial distance r. So hypotenuse is x, sigma z. We are looking at sigma suffix z, and q is the line load. So it's a load which is on the ground and which comes out and hits you. That's the line load. So q per unit length is the line load. So let's take an example. Q has the units of kilonewton per meter. Okay. So what happens to sigma z? That's the expression for sigma z over here. Okay, x again is the hypotenuse. So I can say x square equals to z square plus r square. So I have this equation over there. Again for line load, I would like you to take this as a tablet and remember. Okay. The next one is rather easy. Don't look at the equation because there are design charts, and let me explain this first. This equation on as a whole is a scary thing, but if you look at the design charts, it's fairly straightforward. For uniformly loaded rectangular area, so if I have a rectangular area which is loaded in this manner, x one direction, y in the other direction, and you're looking at sigma z below the corner. Remember, this is one corner. I'm looking at sigma z at this depth z. What is this value? Sigma z is given by this whole lot. Okay, now we are not going to remember this. Fortunately, we don't need to remember. But what we need to think is m n are are normalized dimensions of the loaded area. So m is x by z, so it's one dimension divided by z. N is the other dimension divided by z. Okay, so y by z. Both m and n are interchangeable, meaning I can swap the two. I can make m equal to y by z and n equal to x by z. So I can swap them. Okay, and q is the pressure on the surface. Okay, and sigma z is at any depth. Now I can plug in the values and derive what is sigma z. But fortunately, Bossy came out with design charts, and we are going to look at this design chart. It's available in almost every standard textbook on soil mechanics, and we'll just look at this very carefully, how this chart looks like. Now in this case, before you in fact start looking at it, on the left hand side you'll find an equation or an expression. Fortunately, again, this equation or expression is always available on the chart. I don't think you can read this very carefully, but it's the same thing over here. Sigma z is the stress at a depth below corner of the footing. A footing has dimension of x and y. Okay. Someone says presenter audio not clear. I'm trying to be, yeah, it's clear. Okay. Okay, so sigma z is again q times I, which is the influence value. Sigma z is stress below depth, below corner, and q is the whatever is the pressure you apply on the surface or on the footing. Okay, I is the influence value. I have to zoom out again because I have to explain this. So, yeah, let's put the page. Okay, as you suggest, I've zoomed it slightly. Okay, so this I is the influence value which is read from these charts. These are charts, design charts which we look at. Value of horizontal axis is the n value. Okay, so n is the normalized one part of the dimension of the loaded area, and each curve represents the m value. Again, m. And remember, we said you can interchange the curves. M and n are interchangeable. You can interchange them. The vertical axis or the ordinate axis is the influence value. So my job is to first derive what is n and m for this case, okay, and then read n and corresponding m, and then strike a point on this chart, and then read the horizontal value. This horizontal value is the influence value. I directly plug this influence value in this equation. So influence value times the loaded area will directly give me the stress at a depth, sigma z. Okay. Now it's as straightforward as that, but there's a rider. What happens if this point is not corner? If it is within the loaded area? In this case, if it is within the loaded area, I need to divide this loaded area into smaller rectangles or smaller squares, such that for each square or rectangle, my point is at the corner. Remember, this chart is only valid if your point is at a corner. Okay, so I have to subdivide this such that the point is at the corner, and then derive or solve my sigma z value for each and every smaller rectangle, smaller square, and then add the results. Remember, this is elasticity, principle of superimposition works, so I can add them up. Another part of stress spectrum can be what happens if this point is outside the loaded area. Okay, in this case, I assume the loaded area to be larger such that the point is again at a corner. Okay, and then subtract these smaller area such that then you have the answer. Now, it will be easy for us to understand if you do a problem. I have lined up a problem towards the end of this lecture. So we'll do a simple problem to understand this concept. Okay. The next case is again Bossy theory, but this time if you look at the cartoon on the bottom right, it's a circular loaded area. Circular loaded area of radius r. So you're looking at a point which is x away from the center of the loaded area. I have again a case influence value, but in this case the influence value is in percent. That is why we have a divided by 100 over there. And another difference is influence value is now in horizontal scale. Horizontal scale, that's the abscissa scale, and vertical axis is now normalized depth z by r. R is the radius of the loaded area, and each and every curve, okay, represents my x by z, which is again horizontal offset, normalized horizontal offset. I would like you to go home and look at these charts carefully, because in this line we have another chart again for a trapezoidal loaded area. I would like you to go home and look at this, what are A and B, and you're again looking at sigma z from this chart. Okay, it's again there's no rocket science to understand this, but as long as this figure is clear to you. In this figure, the loaded area trapezoidal, the triangular loaded area is A, B is the other end. This fine example of this loaded area would be your embankment. So that's the edge of the embankment where it goes down. So in this case, you're looking at sigma z anywhere below the embankment. You can then use this chart. The next one is Newmark's influence chart. I would not do this because I think we are running out of time. But again, this chart is based on a scale. Whenever you see such a chart in any textbook, remember again it's based on Bossy's theory. There will be a scale. This scale is shown on the figure at the bottom. Let me quickly zoom in, although I thought of skipping this. But this scale at the bottom of the figure, you need to scale your z, the depth or the point you're looking at below surface or below the footing. You need to scale that z distance with this value, okay, and then redraw your loaded area. Okay, redraw the loaded area onto this point, onto this scale, and then count the number of rectangles, whether complete or incomplete. I think this will confuse you. Let me skip this. In fact, this was not part of the original deal. I'll skip this new chart for the time being. It'll just confuse you. Vestergaard is again based on similar principle as Bossy. So it's also based on theory of elasticity. The only difference in Westergaard and Bossy's theory is that Westergaard takes layered deposit. So it's excellent if you have take an example of warped clay. Warped clay is layered deposits of clay and silt. So it will be excellent example for warped clay, Westergaard solution. In fact, some of you who do ground improvement works using GeoGrid. So if you use GeoGrid, Westergaard solution would be an excellent example for stress distribution. Okay, so you're looking at layered deposit. The only thing over here is the in Westergaard solution only permits vertical movement, no horizontal movement. In other words, if I do not permit horizontal movement, look at the definition of Poisson's ratio. I hope you are aware Poisson's ratio is defined as a ratio of horizontal strain to vertical strain. If I in Westergaard's solution, since horizontal deformation is not permitted, in other words horizontal strains will be 0. In other words Poisson's ratio for Westergaard is 0. In the usual case I have just given a liner, it is not related to this slide, but in the usual case Poisson's ratio for our routine soils, sand, silts, is usually 0.2 to 0.4, and for saturated clays it's taken as 0.4 to 0.5. Okay. I'm not going to go into these details, but that was just a liner just for you to make a note that what is the usual value of Poisson's ratio. Normally if I have to plug in a value, assumed value I would take as 0.27. If I take an undrained case is by default I will take Poisson's ratio as 0.5. Okay. So Westergaard, like I said, its solution is similar to Bossy. So if I'm looking at a point load on the surface and stress distribution below, this equation is not very much different than Bossy. So I have 1 plus 2 r by z whole square. I can actually play around with z. I'll find that this term or this equation is not very much different than Bossy. Okay. Again, I would like you to take this equation as a tablet. For the distributed area, again a rectangular distributed area, a corner, I have a chart which is very similar to Bossy's theory. This chart is for Westergaard. Remember I have n and m parameters on this curve, and I can select them so that accordingly I get the influence value which is read from the vertical axis. I'm not sure if you can read these values on your PowerPoint projection, but once you go home please download this file and then you can go through this presentation at leisure. Okay. This was the only way I could influence display the whole figure onto one single slide. So to conclude or summarize this work, we say Westergaard's assumption usually are much closer to or much more practical for layered deposits. However, both the theories are based on theory of elasticity, which is again far from the correct theory. Soils are not elastic. It will never come back to its original state. It's not elastic. Okay, there are other cases. We will probably do a bit on this, do a superficial work on this when we look at consolidation and shear strength. But bottom line is soils are not elastic unless you're dealing with over consolidated or dense soils. Okay, so that's one aspect which is different. But it boils down to a matter of personal preference. What do you prefer? How do you want to use it? That's the one. But towards the beginning I said the 2:1 method is probably the most commonly used. Okay. Now in the next slide I have lined up one problem, and I'll probably touch this problem later, but you can download this question, it's part of it. I like to do the second problem first. Okay, just skip this. I like to do the second question first. Okay, please go through this question. Just quickly give a quick read. Do not copy. You can download this when you go home. I'll explain this question, what this question is about. Is it visible? Visible? Okay, thank you. So this question is what it shows is it's a rectangular loaded area with a hollow. That's the hollow region in between. and in between the hollow region at the center is the point A, and you're asked to find out what is the stress below ground at this point, which is sorry, where's the point? 2 meters below the center. So you're looking at meters below this, so it's normal to the paper, it goes out inside the paper, 2 meters below the paper. What is the vertical stress sigma V? That's the question. And I think the dimensions of the footing are given, so it's a 2 meter square, empty square, 5 meter, 4 meter dimension. Look at this very carefully, and the surface loading Q is 200 kilopascal. That's the question. Okay. So remember, what we said was, the if it says use Bossy chart. If you have to use the chart, which is here. Yep, that's the chart over here. My point should be below the corner. That's the corner. I'm looking at corner. Irrespective, I'm looking at this corner, that corner, that corner, or this corner. It does not matter. I'm just looking at the corner. That is important to understand. So, however, in this example, the loaded point or the point I'm interested in is somewhere within the I would say within the loaded area, but within the hollow region. So it will be easy for me to understand if I divide this footing into parts. So if that is the point, I'm going to divide this, remember, in parts. That's one part over here, a second part over here, a third part over here, and the fourth part over here. So let me call this as, for example, call this as first part. I'm going to shade this region. So that's my one part. And because this is also, I assume, I'm going to shade this out right now. So I'm going to take this entire area, find out stress distribution at this corner, and then subtract this smaller area. Okay? Remember, theory of superimposition works. Likewise, I'll take this entire area, okay, that's the corner, and then subtract this smaller area. Right? I can do the same thing for the bottom two parts. The only thing is, common sense tells me the bottom two are the mirror image of the top. Okay, so you got to think very clear when you do this. The bottom two are the mirror image, so I just need to solve the upper two, and then whatever the answer I get, I multiply by 2. Okay, so just to put everything in words, you're going to solve this question, okay, over here. Okay, we say the center of the hole, the center of the hole is outside the loaded area. Okay, therefore, it is convenient to divide the loaded area such that the point A lies at the corner of the loaded area. Okay, that's one. We can then the area or the squares that cover the hole can then be conveniently be deleted. Okay, and the third thing which we have taken for this figure is, because of symmetry, comma, only the top or upper half of the footing is considered. Okay, so these are the 3 points, or just we have just put it in English. I hope my handwriting is not so poor and you're able to grasp, but it's just to put it in English what we have just said. So if you have a faster hand, you can jot it down, but it's just to put it what we have just said, that we have divided this into a number of parts and then subtract the empty part, and we will only consider the top half. So for this, let me just draw the figure. Okay, I'm going to change this page. Okay, let me draw the figure. The figure is, that's the hole. I'll just jot down the dimension. It's 4 meters, 5 meters. This whole thing is 1 meter. That's 2 meters. 1 meter is this. 2 meters is this thing. And 1 meter is this dimension. Okay, and this is the point you're interested in. We said we are going to divide this into area. Okay, and I'm going to only look at the top half. So can I say this is equivalent to just the top half? Mind you, I'm just looking at the top half. So this whole dimension, this dimension is 1 meter. This hole was 2 meter deep, and this point is the center. In other words, this dimension is also 1 meter. So from there to there is 2 meters. So this whole dimension is 2 meters. This dimension over here is again 1 meter and 1 meter. So that dimension is also 2 meters. And that's the point A. Okay, so that's the first one, first area, this whole thing. I have to subtract this smaller area, this small area. So this minus the smaller area, which is this whole thing. Remember, this is 1 meter and that's 1 meter. So it's 1 by 1. Again, I'm looking at the corner, which is over here. Let me call this as X, this as Y. Okay. Now I'm looking at this big rectangle over there. This big rectangle will have a dimension, so it's okay. This is 2 meters. This whole thing is 1 plus 1. So it's 2 meters from this end to this end. So the remaining would be 5 minus 2. This is 3 meters. So I have plus. That's the 3 meters for me. What about this dimension? It's 1 meter plus another 1 meter. So it's 2 meters. And the point is here. That's the A point. It does not matter where the A point is because you're still looking at corner. It has to be at the corner. And let me call this as Z. So I have taken this whole Z, this whole thing. What I need to do is subtract the smaller area. This small area is minus, okay, small area, it's 1 meter by 1 meter, and the corner is here, A. If you look at this small rectangle, again it's similar to this rectangle. Okay, it's the same thing, similar. I'll put this as Y again. Okay, the only thing is A point is different. That's of course permitted. It's permitted. So the next job is to read out the values. So I have this area A. I would like you to draw a table. So that's area. The first area is X. Okay. Then the dimension L. Okay, let me just say this is meters. B is again meters. So the first area X, L, I can take arbitrarily any value, either this value or the other value. It's 2 meters. B is 2 meters again. Okay, what's the next one? M. M and N. Remember, M and N are the dimensionless, or I would say normalized parameters of the dimension of the footing. So M equals to L by Z and N equals to B by Z. Remember, I could interchange. I can take M as B by Z and N as L by Z. It would not matter. So in this case, I'll take this numeric value is similar. I'll take M as 2 divided by the depth is again you're asked to find out what is the stress at 2 meters below. So that was the 2 meters. So Z in this case is 2 meters. M is equal to X by Z, N equal to Y by Z. In this case, N is also 1. Next is the influence value, which I need to read from the chart. Now, I'm going to just quickly show you the chart, but I would like you to go home and read it, Let me see if I can zoom this, at least for the first one. Okay, stop here. So, I have N on the horizontal axis, and both M and N are 1. So, this is starts from 0.01, that's the 1 value. So, I need to go up. M is also 1. M is 1 somewhere here. So this is the curve of M for 1. The intersect of this point is somewhere here. I need to read out this value. Okay, in this case, the value of I is 0.179. Okay, I cheated. I took a hand lens, and before coming over here, I actually value. You can go home and look at this very carefully. But I have a value of 0.179. Okay. So what is if this influence value is 0.179, what is sigma z? Remember, sigma z is kPa. None of these have any units. Sigma z is kPa, which equals to the applied load, which is 200 times 0.179. So 200 is given to us. Okay, 200 is here given to us. So 200 times 0.179 should give you 35.8. Okay, I'll just write positive because this load is to be added. Likewise, the second area Y is this Y. Each dimension is 1, depth is 2, so L is 1, B is 1. What about M and N? Depth is 2, so 1 divided by 2 is half. 1 divided by 2 is half. So again, I need to read out, take the chart, go and pick up the chart value. Take a value of half, which is over here, and half, which is along this curve. And if I read very carefully, that's the point. And I would like you to go home and read this value. Okay, this value I have again cheated. I took a hand lens at home, and I read this value carefully from the figure. You can use your eye judgment. You may not have to carry a hand lens every time, but an approximate value, a good approximate value should really help you or give you a good answer. The final one is influence value times 20. In this case, which is influence value times 200. So it's 0.085 times 200, which is 17. And remember, this has to be subtracted. So I've just written minus for my convenience so that towards the end I do not forget to subtract this value. The third area is Z. This is this area. It has one dimension of 3, the other one 2. So I'll just write 3 over here, 2 over there. Doesn't matter if I just write 2 over there or 3 over there. M is 3 divided by 2, which is 1.5. N is 2 divided by 2, which is 1. Again, I read the influence value of 1.5 to 1. Okay, let me see if I can show you the figure. So 1 is there, 2 is there, so 1.5 would be somewhere here. Remember, this is log scale, so 1.5 should be somewhere beyond the approximate middle value. And M value is 1. So 1 is somewhere there. So that's the point I'm looking at. I could have also done it the other way. I could have taken a 1 value from here and read 1.5 from there. See 1.2, 1.3, this is 4, so 1.6. Only thing is these lines get too narrow and it becomes difficult for me to read 1.5. So it will be much easier if I take the 1.5 along the horizontal axis, which is wide. It helps me to read. It becomes narrow over there. So the idea of interchanging m and n is helpful for me to read out the figure. Okay, so like I said, I cheated. I went home, took a hand lens and read this value. I would like you to go home and read this value of influence value from the chart, which should give you a number which is 0.196. Okay, so the idea is 0.196 times 200. This should give you a sigma z value of 39.2. Again, I'll write positive so that I do not forget that this value is to be added. Okay, so the last one is area y, which is again y again. I need not write this or read it down again because same as this line. So I'm quickly going to copy these from the above. Okay, 0.085 from there, 17 from there, and remember, I will not, let me zoom out. Sorry, I had zoomed in. Let's zoom out. Who's zooming? I'm zooming. Okay, stop. So this 17 is again negative, okay, because it's subtracted from the bigger area. If I add these up, 35.8 minus 17 plus 39 minus 17, I should get an answer which is 41 kilopascal. So the total vertical stress component, okay, at A should be equal to 2 times summation of sigma v, right? This I have done 41 over there, so it's twice of 41. Remember, we said the area. Where is the figure, please? Yep. We only look at the top half of this loaded area. The bottom half we said is mirror image. So I'm going to take 2 times of sigma v, which gives me a value of 82 kilonewton per meter square or kilopascal. Okay. That was question number 2. So if you're happy with it, I would like you to go home and try question number 1. Can I have this slide again, please? No, no, it's here, right? This is, no, I would like to see the monitor, not this. Yeah, is it? Okay, so this the question 1 which you just missed is an easier one. What it says is there are 2 circular footings. Okay, so they are placed at a distance a apart and you're looking at a point z below ground. You're asked to find out, so what should be the spacing. So you're looking at spacing of a such that the stress below ground at this point is not more than 20% of the load at the surface. Okay, I want you to try this at home. I will go to next slide, which shows the chart which would be useful for this particular slide. Remember, it's a circular footing. You're asked to find out what is x. Everything else is given. The influence value is given. Influence value can be reduced. It says it should not be more than 20%. Both the z and r are given. Also, you would have to read out this value of what is the x by r value. This should give you the spacing. It's an easy question, much easier than, I would say relatively easier than what you have just tried. I would like you to go home and try this. Okay? We have slightly less than 5 minutes remaining. If you have any question, please ask them. We have a luxury of 5 minutes. Was it so clear? No question? we always say, was it crystal clear or muddy clear? Is it crystal clear or muddy clear? Any question? Or let's open up a camera. किसी को push करते हैं, push someone to ask. There's one. It's empty room. Yeah, I think they're close. Okay, there's a question from AITM teacher. Yes, please.
Good morning, sir. Hello.
Good morning.
Sir, I am Hanumantra from Aditya Engineering College. Sir, how sigma z varies in case of this poorly graded soils and well graded soils, sir? How the sigma z varies?
How does, okay, the question is, how does sigma z vary for poorly graded soil and well graded soil? Okay, I must
Yes,
admit your
sir.
questions are very tricky. Okay, I don't think, if you follow this, the principle which we have just used, it does not matter, because all the theory which we use for stress distribution, it assumes that the soil is continuum. Now what does this continuum mean? Continuum means that the material is continuous, it's no longer porous. So if you look at the soil gradation, whether it's poorly graded, well graded, they all speak about soil porosity. There is some pores. All the stress distribution which we use in our soil mechanics, it assumes that the soil is continuum, and the basic assumption of continuum is there is no the porosity, it's continuous, one single material. So I would say your question is good, but I have no answer, because when you look at the distribution, the fact that whether it's porous, whether it's well graded, how the grain size are, it does not matter. But you have a logic over there, because in IS code it says whether based on what kind of soil you have, the stress distribution, there is variation in the stress distribution, the angle of dispersion. So it recommends whether you take 30 degree, 45 degree or 60 degree. So in this case I would say you please refer to those, those particular distribution curves. That too only varies for 2:1. Remember the 2:1 which we had, but it does not follow the the other distribution or the other charts. But bottom line is, my sincere, my own suggestion would be just to obey the 2:1. It makes our life much easier. Okay, I hope I was able to answer your question. There's no reaction from your end either. I don't see any reaction.
Sir, sir, just now you discussed about the load outside the shaded area. So how the pressure valve varies? How the this load outside the shaded area? How it varies? How the pressure valve varies? That means what I am asking is what is the effect of the load outside the shaded area on the pressure
Okay.
valve? That is what I am asking.
Okay, I have not plotted this with depth, but I would still not be wrong to suggest that, if you look at the Bossy stress distribution for a point load and the load on which we had a footing, there was a foundation, and the pressure bulbs which were computed, those pressure bulbs, you would not be wrong to look at the distribution using pressure bulb. So I would say it's still distributed. It will still decrease with depth. Okay.
Okay, sir. Okay, thank you.
Thank you. The mouse has gone in. Right? That's a question. I didn't understand. There's a GNTUA. We have exceeded our time, which says give Westergaard's theory. I don't understand what's the question. What does it mean? I guess it's incomplete. But could you please post your question onto your on an email, because I think this question appears to be incomplete. Okay, we have the next instructor over here, and I'm sorry I have to stop right now. Thank you very much. Bye.